never dreamed that one day
Hi there everyone, welcome to the third lesson on Surds. In this lesson, we want to look at two more standard techniques for Surds. These are rationalizing the denominator and proving identities. Before we look at examples for this lesson, let's look at what we mean by rationalizing the denominator. The square root of 3 is an irrational number, so this is irrational. Since 3 is not a perfect square, the square root of 4, on the other hand, is a rational number, since 4 is a perfect square. Likewise, the cube root of 8 will be rational, since 8 is a perfect cube, while the cube root of 2 will be irrational, since 2 is not a perfect cube. Now, we often have fractions where the denominator is irrational. To take an example, let's say we have 3 over the square root of 5. The square root of 5 is irrational since 5 is not a perfect square. Another example, let's say we have 2 over 3 minus the square root of 7. Here we have two terms in the denominator, but the square root of 7 is irrational, making the whole denominator irrational. Now, it's often convenient for us to remove the surd from the denominator. In other words, it's convenient often to write the denominator of a fraction as a rational number. And in this lesson, we want to look at how to do that. In example 2, it says, write each of the following with a rational denominator. Simplify first where necessary. Let's look at the first expression. So we have 2 over 3 times the square root of 2. Now, the denominator here is an irrational number because the square root of 2 is irrational. And we want to write this fraction with a rational denominator. In other words, we want to eliminate the surd in the denominator. So we simply multiply both the numerator and the denominator by the square root of 2. So we're multiplying the entire fraction then by square root 2 over square root 2. Then multiplying the numerators, we have 2 times the square root of 2, so 2 square root 2, and then multiplying the denominators, 3 root 2 times root 2 is 3 times 2. And here we are using the surd law that says the square root of a times the square root of a is a. So the square root of 2 times the square root of 2 equals 2. We can cancel the 2's and we're left with the square root of 2 over 3. We've managed to remove the surd from the denominator. So the denominator now is a rational number. Note that the square root of 2 over 3 is the same as 2 divided by 3 times the square root of 2. So this fraction here is the same as the fraction that we started with. We have just managed to rewrite it without a surd in the denominator. Let's look at the second expression. So we have 2 over 3 minus root 7, and root 7 is an irrational number, which makes the entire denominator here irrational. And we want to rationalize the denominator. In other words, we want to remove the surd from it. In this case, we have two terms in a denominator. So what we do is we multiply this fraction by something that will give us a difference of squares in the denominator. And this is going to be 3 plus root 7. So when we multiply the denominators here, we're going to get a difference of squares. And we also have to multiply the numerator by 3 plus root 7. Then just bear in mind that if you have a minus b times a plus b, it's going to be a squared, in other words the first term squared, minus b squared, the second term squared. So when we multiply the denominators here, we get a difference of squares. A minus b times a plus b. So we square the first term, 3 squared is 9, minus, and we square the second term. The square root of 7 squared, of course, is 7. So here we multiplied the denominators. Now we can multiply the numerator, or numerators. So it's 2 times 3 plus root 7. And of course we have 2 into 3 plus root 7 on top. And in the denominator, we have 9 minus 7, which is 2. And these factors cancel. And we're left with 3 plus root 7. And 3 plus root 7 is the same as 3 plus root 7 all over 1. And 1, of course, is a rational number. So we have managed to remove the surd from the denominator. And the denominator now is rational. Coming to number 3, we have 2 minus root 3 over 2 plus root 3. And we want to rationalize the denominator. So once again, we multiply both the numerator and the denominator by something that gives a difference of squares in the denominator. In this case, by 2 minus root 3. Now when we multiply out the denominators, we'll get a difference of squares. So it's a first term squared, 2 squared, which is 4, minus a second term squared, and the root of 3 squared, of course, is 3. We must also multiply out the numerators, and this will be squaring a binomial. And recall that a minus b all squared. So squaring a binomial is the first term squared minus twice the first term times the second term plus the second term squared. So applying it here, when we multiply out the numerators, it's a first term squared, 4, minus twice the first term, so twice 2, times the second term, so times the square root of 3, plus the second term squared. And the square root of 3 squared, of course, is 3. Now, in the numerator, 4 plus 3 is 7. And negative 2 times 2 is negative 4. So negative 4 root 3 all over 1. So we have removed the surd from the denominator, and the denominator now is rational because 1 is a rational number. Let's look at number 4. We have the square root of 45 over 3 plus the square root of 5. And we want to rationalize the denominator. Before we do that though, we can simplify the numerator. The square root of 45 we can write as a square root of 9 times 5. 9 is the largest perfect square that goes into 45. And this can be written as a square root of 9 times the square root of 5, which is 3 times the square root of 5. So in the numerator we have 3 times the square root of 5. Now we can rationalize so we multiply both the numerator and the denominator by 3 minus root 5. So something that will give a difference of squares in a denominator. So now we multiply out the numerator and the denominator. In the denominator, we have a difference of squares, so it's 3 squared, which is 9, minus root 5 squared, which is 5. And then we multiply out the numerators, so 3 times 3 is 9, so we have 9 root 5, minus root 5 times root 5 is 5, and we also have the 3 here. So 3 root 5 times root 5 is 3 times 5. And this is 9 root 5 minus 15 all over 4. And now we have managed to write the denominator as a rational number. And we can't simplify any further here, so this is our answer. In number 5, we have 2 terms. So the way we're going to deal with this is to rationalize them separately. So for 1 over square root 2, we can rationalize by multiplying both the numerator and the denominator by square root 2. Then for the second term, 1 over 1 minus the root of 2, we multiply both numerator and denominator by 1 plus the square root of 2. So then in the first term, 1 times root 2 is root 2, and root 2 times root 2 is 2, so we've rationalized the denominator here. Then in the second term, 1 times 1 plus root 2, and in the denominator, we have a difference of squares now. So it's going to be the first term squared, so 1, minus the second term squared, which is 2. So then we have root 2 over 2. And of course, 1 minus 2 is minus 1. And a minus times a plus is a minus. So it's 1 plus root 2 here over 1. Now we can simplify. We can write everything over 1 LCD. The LCD, of course, is 2. So 2 into 2 once times the top. And then 1 into 2 twice times the numerator. And we're going to need brackets here because of the minus. So 1 into 2 twice times 1 plus root 2. So we're simplifying. So we have root 2 minus, we can multiply the 2 into the brackets. So root 2 minus twice root 2 is minus root 2. And then we also have minus 2 left in the numerator. And this is the simplest form. Let's look at the last expression. So we have the square root of 75 minus the square root of 27 all over the square root of 24. And before we rationalize, we're going to simplify this. Now, the square root of 75, we can write as a square root of 25 times 3. 25 being the largest perfect square that goes into 75. And this is a square root of 25 times the square root of 3, which is 5 root 3. So we can replace the square root of 75 with 5 root 3. Then the square root of 27, we can write as a square root of 9 times 3, which is a square root of 9 times the square root of 3, which is 3 root 3. So 3 root 3. Then the square root of 24. The largest perfect square that goes into 24 is 4. And it goes 6 times. So we can write this as a square root of 4 times the square root of 6, which is twice the square root of 6. So twice the square root of 6. We can add like terms in the numerator. 5 root 3 minus 3 root 3 is 2 root 3. And in the denominator we have 2 root 6. So these factors can cancel. The 2's can cancel. And we're left with root 3 over root 6. Now we can rationalize. So we can multiply both the numerator and the denominator by root 6. So in the denominator, root 6 times root 6 will give us 6. And in the numerator, we have root 3 times root 6, which is root 18. Now, we're using the rule here of Surds that says the root of A times the root of B is the root of AB. Now we can simplify the root of 18 further by writing it as root 9 times root 2. 9 being the biggest perfect square that goes into 18. This is over 6. And the square root of 9, of course, is 3. So we have 3 root 2 over 6. And 3 into 6 twice. So it all reduces to the square root of 2 over 2. Let's look at your answers to this question. In the first one, we have 15 over 2 times root 5. And we want to rationalize the denominator. So we multiply both the numerator and the denominator by root 5. So then multiplying the numerators, we get 15 times root 5. And in a denominator, we get 2 times root 5 times root 5 is 5. The 5 can go into the 15 thrice. And we're left with 3 times root 5 over 2. In number 2, we have 12 divided by 2 minus root 7. And we want to rationalize the denominator. So we multiply both the numerator and the denominator by 2 plus root 7. So 2 plus root 7. Then 12 times 2 plus root 7 is 12 into 2 plus root 7. In the denominator, we have the difference of squares. So we square the first term minus the square of the second term. So it's 12 into 2 plus root 7, and this is over 4 minus 7, which is negative 3. The negative 3 can go into 12 negative 4 times. So we're left with negative 4 into 2 plus root 7. And now we can multiply out, so we get negative 8 minus 4 times root 7. In number 3, we have 3 minus root 2 all over 3 plus root 2. We want to rationalize the denominator, so we multiply both the numerator and the denominator by 3 minus root 2. In the denominator, once again, we have a difference of squares. So it's 9 minus 2, the square of the first term minus the square of the second term. In the numerator, we have to square out the binomial. We have 3 minus root 2 all squared. So once again, a minus b all squared is a squared minus 2ab plus b squared. So applying this to the numerator, we have the first term squared minus twice the first term, so twice 3, times the second term. And then we have plus the second term squared, so root 2 squared. So we have 9 plus 2 here in the numerator, which is 11, minus 6 root 2. And this is all over 9 minus 2, which of course is 7. And this is the final answer because we can't simplify this any further, and the denominator is now a rational number. Then in number 4, we have 24 over the square root of 96 minus the square root of 24. Before we rationalize here, we're going to simplify the terms in the denominator first. So we have 24 in the numerator, and then the square root of 96 we can write as a square root of 16 times 6. 16 is the biggest perfect square that goes into 96. So this is square root 16 times square root 6, which is 4 square root 6. So we have 4 square root 6. Then 24 we can write as the square root of, or the square root of 24, we can write as the square root of 4 times 6. 4 being the biggest perfect square into 24. And this, of course, is square root 4 times square root 6, which is twice the square root of 6. We can add like terms in the denominator. 4 minus 2 is 2, so we have 2 root 6 left in the denominator. Then, of course, 2 can go into 24 12 times. So we have 12 divided by square root 6. And now we can rationalize. We multiply both the numerator and the denominator by square root 6. So 12 times square root 6 divided by square root 6 times square root 6 is 6. And 6 goes into 12 twice. And our final answer then is 2 times the square root of 6. Let's look at the last expression here. Here we have two terms, so we're going to rationalize them separately. So the first term is 1 over root 2 plus 2. And we can rationalize the denominator by multiplying both numerator and denominator by root 2 minus 2. So root 2 minus 2. Then in the second term, before we rationalize, we're going to simplify first. We know that the square root of 8 can be written as a square root of 4 times 2, and this is 2 root 2. So then we have 2 root 2, and of course the 2's cancel. Then coming back to the first term here, 1 times root 2 minus 2 is root 2 minus 2. And in the denominator we have a difference of squares. So we square the first term, minus, and we square the second term. And here we have 1 over root 2 in the second term, which we can rationalize now. So we multiply by root 2 over root 2. So in the first term we left with root 2 minus 2 all over negative 2. And in the second term we have 1 times root 2, which is root 2, over root 2 times root 2, which is 2. We can simplify further. We can divide the negative into the numerator here, and we get 2 minus root 2 over 2. So we switch around the terms, and we still have minus root 2 over 2. We can write this as one fraction. The LCD, of course, is root 2, or rather is 2. And then we have 2 minus root 2, and then minus root 2. So we have 2 minus twice root 2 left in the numerator. When we add like terms, we can take out a common factor in the numerator of 2. 2 into 2 once, minus 2 into 2 root 2, we're left with root 2. This is all over 2. And the 2's cancel. So we're left with 1 minus the square root of 2. And now the denominator is rationalized, because this can be written over 1, and 1 of course is a rational number. So example 3 deals with proving identities. It says, without a calculator, prove that the following is true. And we are given this equation. So let's have a look at it. We start with the left-hand side. And we basically simplify the left-hand side. Now, the square root of 27 we can write as a square root of 9 times 3. 9 is the biggest or largest perfect square that goes into 27. And this we can split up as a square root of 9 times the square root of 3, which of course is 3 times the square root of 3. So we have 3 times the square root of 3 less the square root of 3 in the numerator. We can add like terms in a numerator. So 3 root 3 less 1 root 3 is 2 root 3. Now we can rationalize the denominator. So we can multiply both the numerator and the denominator by 3 minus root 3. So 3 minus root 3. When we multiply out the denominators here, we're going to get a difference of squares, which is what we want. So multiplying the numerators in these two fractions, 2 root 3 times 3 is 6 root 3. And we have 2 times root 3 times root 3, which is 3. Multiplying out the denominators, we have a difference of squares. So the first term squared is 9 minus, and the second term squared is 3. So it's 6 root 3 less 6, all over 9 minus 3, which is 6. And we can take out a common factor in the numerator. So we're left with root 3 minus 1. And this is all over 6. And the 6's cancel. And our final answer is root 3 minus 1. Now, this is exactly the right-hand side in this equation. So we can say that it's equal to the right-hand side. So we have proved that the left-hand side equals the right-hand side. And hence, this equation or identity is true. So let's look at your answer to question 3. It says, without a calculator, prove that each of the following is true. And we are given these 3 identities. So let's look at the first one. We start with the left-hand side. And we're going to simplify as much as we can. Now the square root of 80, we're going to write as a square root of 16 times 5. 16 is the largest perfect square that goes into 80. And we're going to split up the surd into the square root of 16 times the square root of 5. And this is 4 square root 5. So 4 square root 5. We can add like terms in the denominator. 4 square root 5 minus 1 square root 5 is 3 square root 5. And a 3 can cancel into the 15, goes 5 times. And we are left with 5 over square root 5. Now, let's go back and see what we needed to prove. That the left-hand side comes to the square root of 5. And this is not quite the square root of 5. So we're going to rationalize the denominator. We're going to multiply both the numerator and the denominator by the square root of 5. So we have 5 times the square root of 5, which is 5 square root 5. And multiplying the denominators, the square root of 5 times the square root of 5 is 5. And the 5 can cancel. And now we are left with the square root of 5, which is in fact the right-hand side. So we have now proved the identity. Let's look at the second identity. So once again, we start with the left-hand side. And we're going to simplify it as far as possible. So the square root of 8, we can write as a square root of 4 times 2, which is a square root of 4 times the square root of 2, and this is twice root 2. So then we have the square root of 3 minus twice the square root of 2 plus twice the square root of 2 minus 1. And immediately these two terms can cancel in the numerator. Then we're also going to rewrite the square root of 12. So the square root of 12 as a square root of 4 times 3. 4 is the biggest perfect square that goes into 12. And this is square root 4 times square root 3, which is twice square root 3. So we have 2 times the square root of 12. So 2 times twice the square root of 3 will give us 4 times the square root of 3. Then similarly, we're going to rewrite the square root of 18. So the square root of 18 is the square root of 9 times 2. And this is the square root of 9 times the square root of 2, which is thrice the square root of 2. So we can replace the square root of 18 with 3 times the square root of 2. And of course, these two terms can cancel in the denominator. So in the numerator, we're left with square root 3 minus 1. So square root 3 minus 1. And in the denominator, we can add like terms. 4 times the square root of 3 minus 3 times the square root of 3 is 1 square root 3. Or just square root 3. And then we still have plus 1 left in the denominator. Now, this is not quite equal to the right-hand side, as you can see. So we're going to rationalize the denominator. We're going to multiply both the numerator and the denominator by square root 3 minus 1. In other words, by something that gives a difference of squares when we multiply out the denominators. So then, multiplying out, first the numerators, we have square root 3 minus 1 times square root 3 minus 1. This is a binomial squared. So we'll have square root 3 minus 1 all squared in the numerator. And we know that this is the first term squared, which is 3, minus twice the first term times the second term, plus the second term squared, 1 squared. And 3 plus 1 is 4. So 4 minus twice root 3. So then multiplying out the numerators give 4 minus twice root 3. This over here. Then multiplying out the denominators, it will be a difference of squares. So we square the first term minus, and we square the second term. So we're left with 4 minus twice root 3 over 3 minus 1, which is 2. Now we can take out a common factor of 2 in the numerator. So 2 into 4 twice. So we have 2 minus root 3 all over 2. And of course, the 2's will cancel. So we are left with 2 minus root 3. So the left-hand side then, the left-hand side reduces to 2 minus the square root of 3. Now to go back to the identity, this is exactly the right-hand side of the identity. So we can say that this is equal to the right-hand side. And we have now proved the identity. Coming to the last identity here, once again, we start with the left-hand side. In this case, we don't have an algebraic fraction, so we can't rationalize the denominator. Now, what you may be surprised to know is that we can also rationalize the numerator, which is what we're going to do now. We're first going to write the left-hand side as a fraction, as over 1. And we're going to rationalize the numerator now. So we're going to multiply both the numerator and the denominator by something that will give a difference of squares when we multiply out the numerators. So by the square root of n plus 1 plus the square root of n. So let's multiply out the numerators. It'll give a difference of squares now. So we square the first term. We square the first term and the square root drops. So n plus 1 minus we square the second term and the square root drops. So we're left with n. These two can cancel. And then multiply out or multiplying out the denominators, 1 times the denominator here will give us square root of n plus 1 plus the square root of n. So this is 1 over the square root of n plus 1 plus the square root of n. Now let's go back to the identity. As you can see, it's the right hand side. So we can now say that the left-hand side equals the right-hand side. And we have proved the identity.